Good morning all. Can you hear me?
Yes, madam.
Okay. Right. So the timetable has been changed, isn't it? So කලින් දන්නවන්නේ නේද ලෙක්චර් එක මේ වෙලාවට තියෙනවා කියලා?
Oh, madam.
Yes, madam.
Hari. Okay. So under this course, we have finished 3 chapters. First one, the introduction to probability, the basic things, and then about the random variables, and then the discrete probability distributions, right? So under the discrete probability distributions, we learned 7 distributions, namely uniform distribution, Bernoulli, binomial, geometric, negative binomial, hypergeometric, and Poisson distributions, right? So as the first one, we learned the uniform distribution. Under the uniform distribution, the random variable follows discrete uniform distribution, X follows a discrete uniform distribution with parameter n, capital N, right? In the uniform distribution, all the outcome of a trial have the same probability of getting selected, right? That is the discrete uniform distribution. And the second one is the Bernoulli distribution. In the Bernoulli distribution, there are some special properties. In a Bernoulli random variable or a Bernoulli experiment, we said, in Bernoulli experiment, there are 2 outcomes, only 2 outcomes as the success and failure, right? So probability of success P and probability of failure is 1 minus P over Q, right? So it is the Bernoulli random variable, and if the random variable is X, it follows a Bernoulli distribution with the parameter P. So we can write the probability density function, right? And then the third one is binomial distribution. We learned the binomial distribution. So under the binomial distribution, it is an extension of a Bernoulli distribution, right? So it's also a Bernoulli, it's using Bernoulli random variable, but there are more than 1 trials, say n trials. So we are concerning about number of successes out of n trials in the binomial distribution, right? So if we denote the binomial random variable as X, we can denote the binomial distribution as prime NP. So there are 2 parameters n and p. N is number of trials and p is probability of success, right? Then the fourth one is geometric distribution. So in geometric distribution, we are concerning about number of trials we want for the first success. Number of trials we need to do in order to get the first success, right? So if we denote it again as random variable x, it follows a geometric distribution with again the parameter probability of success, right? Probability of success is P. So number of trials we need to do in order to get the first success. So if we extend into R success, not the first success, so it is a negative binomial distribution. So in negative binomial distribution, we are concerning about number of trials for the R success. Number of trials we need in order to get the R success, right? So there, the random variable follows a negative binomial distribution with two parameters R and P. So R is the number of trials, the number of successes, R success, right? Then P is the probability of success. Okay, then the next distribution we learned is hypergeometric distribution. So there is a special property in hypergeometric distributions. The earlier 5 distributions we discussed, uniform, Bernoulli, binomial, geometric, and negative binomial, they all have independent trials, right? The second trial is independent of first trial. Third one is independent of second. Likewise, the trials are independent in these 5 distributions. But in hypergeometric distributions, trials are not independent. We discuss it using marble example. We get marbles out without replacing. So in that case, the trials are not independent, right? So in hypergeometric distribution, we are concerning about, we have the population. So in the population, there are m successes, altogether m trials and m successes. So there are n minus 1 failures. So if we take out simple n number of samples out, right? N number of samples out. So what should be the probability out of simple n sample, x, the probability of having x number of successes, right? So that is hypergeometric distribution. That concept follows a hypergeometric distribution if we want to obtain the probability of getting x number of successes out of simple n number of samples, where the population has simple m number of successes out of capital M number of successes out of capital N number of events. Then it has a hypergeometric distribution. We denote the random variable by height, h height. So there we have 3 parameters, right? N, simple n is the sample, and then capital N and capital M. So it is a hypergeometric distribution, right? Then the last one we learned is Poisson distribution. Poisson distribution. So in the Poisson distribution, we consider number of successes during given time interval or space. Right? During given time interval or space, we are concerning about the number of successes. Right? So it denotes using the random variable x, and then it follows a Poisson distribution with parameter lambda. Parameter lambda, right? So parameter lambda is number of success during unit time interval or space. Unit time interval or space. Lambda is that rate, right? So we learned that. So as you can remember, so this is the Poisson, right? Poisson distribution. So we learned Poisson distribution in last lecture, right? So we developed mean, variance, one moment generating function. So we discussed there are two main practical uses, right? One is we can use this Poisson distribution as an approximation to the binomial distribution when n is very large and p is very small. N tends to infinity and p tends to 0. So in that case, we can use the use this Poisson distribution as an approximation to the binomial distribution. And the second use is we can serve this function as a probability distribution function. There, right? We model it for the number of successes that occur during given time interval or space, right? So we learned how to approximate the binomial into the Poisson distribution, right? And then we learned about cumulative Poisson probability tables, how to obtain probability values using tables, and right, and how to serve this as a probability distribution function. Then a corollary, if x has a Poisson with lambda, right? So if we have, so it is for unit time interval. For t units, it follows Poisson with lambda t. And we discuss some examples and then the diagrammatic representation of the Poisson probabilities. So in the diagrammatic representation, we learned special property. When the rate lambda, Poisson parameter lambda, is low, the distribution is skewed, and when it increase, right? When it increase, the property of symmetric is also increased, right? It becomes more symmetrical when lambda increases, right? So then we found the mode of the Poisson distribution. So actually the mode is depend on the parameter lambda. If the parameter lambda is an integer, then there are two modes. If the parameter is lambda, then lambda minus 1 and lambda is the two modes. And if it is not an integer, right? If it is not an integer, the mode is in between lambda minus 1 and lambda. Then we learned how to fit the theoretical distribution. That means we use the experimental result to build up a theoretical distribution and check whether the experimental result follows the Poisson distribution or not. So in order to do that, we want to first fit the theoretical distribution using the experimental result. So we learn how to build up the theoretical distribution. And finally, the summation of two independent Poisson variables. If we have two independent Poisson variables as x and y, then the sum of the two variables x plus y is also follows the Poisson distribution with parameter simple m and simple n. Right? So those are the things we learned under the Poisson distribution. Right? Is there any problem up to this point? So if it is no, we can move to the next section, the chapter 4, continuous probability distribution, right? Continuous probability distribution. Continuous probability distribution. So in the discrete probability distribution, the random variable is discrete, right? But in continuous here, the random variable is continuous. We measure the variable as a continuous variable. As the discrete random variable is not an adequate model in all kinds of probability modeling, we consider the notion of continuous random variables. For example, the following may be taken as continuous random variables whose space are intervals, right? Here, spaces are intervals. That means the data are measurable in as intervals, right? For an example, say this time taken to perform a given task, right? So if we take an interval of time, the random variable can take any value in between that interval. It can take any value, not a discrete value as 1, 2, 3, 4, 5, likewise, but it can take any value between the intervals. The time can take any value, right? So the mass of a quantity packed by a machine, a mass, again we are measuring the mass, right? See? So if we take an interval of mass, suppose for an example, say 1 to 10 kilograms, then the mass can take, or the random variable can take any value in between 1 and 10. Right? If the machine is, the range of the machine is 1 to 10 kilograms, so the mass of the quantity packed by that machine can take, can take any value in between the 1 and 10 kilograms, right? So the third one, a person's waiting time, again a time, it is also a continuous variable, right? So X is capable of attaining any value in some interval and not just discrete points. So that is how we identify whether it is a continuous random variable or discrete variable, right? So if the random variable can take any value in between given ranges or given intervals, it is serve as a continuous random variable, right? So there are many examples. Amount of fuel need to for a vehicle, amount of fuel need to get the full tank, right? Then expenditure at the shopping mall, likewise expenditure, amount of fuel, those kinds of data are continuous data. We can measure those things continuously. That means it can take any value between given intervals. So therefore they are continuous random variables, right? So a continuous random variable is specified by its probability density function denoted by simple fx, where fx is greater than or equals to 0. So these are the things we learned under the random variables. So the probability density function, or the PDF, is denoted using fx, and fx is always equals to 0 or greater than to 0. Then fx is represented by a curve, and the area under the curve within a range gives the probability. So we learned this also under the random variables. So if we denote fx using a curve, then area under the curve gives the probability within the range we want. So in this chapter, you will study some of the probability densities that figure most prominently in statistical theory and applications, right? So we here under the continuous probability distribution part, the chapter 4, we learn special probability distributions as we learned in discrete distributions. as well. So here we are going to learn some special distributions. A function fx is a probability density function for some continuous random variables x if and only if it satisfies the following conditions. So those are those things you know already, right? We learned those things under the random variable chapter. So if x is greater than or equals to 0 for all real x, and if we take the aggregate of all the values, that means minus infinity to plus infinity, it equals to 1. That is the cumulative one, right? Cumulative, the aggregate probability, it's equals to 1. Then probability of the event x that belongs to A, we denote it using x belongs to A. So it can write it as fx dx, right? For any arbitrary point. Okay, that is the introduction to continuous probability. So now this point onwards, we are going to learn special type of continuous probability distributions, right? So as you can remember, in discrete probability distribution, the first one is the uniform distribution. It's the discrete uniform distribution, right? But here, the random variable is now not discrete, it is continuous. Okay, so this is called as rectangular distribution as well. So when we learn the graphical representation, we can understand why it is called rectangular distribution. Suppose that a continuous random variable x can assume values in a bounded interval a comma b, and that the PDF is constant over the interval, right? So in the uniform distribution, x can take values within intervals a and b. Lower bound is a and upper bound is b, right? So in the uniform distribution, it can take only two intervals a and b, right? So within that a and b intervals, the probability density function is a constant. It is, if we denote it as the constant c, fx equals c within the given bounded interval a and b, right? So by using the property b here, see, if we aggregate all the probabilities, it should be equals to 1, right? So within the interval a and b, the probability density function is a constant c. So if we aggregate or get the integration from a to b, it should be equals to 1, right? It should be equals to 1. So we know that by integrating this, right? By integrating this, we can obtain value for c. It is 1 over b minus a, right? So if we integrate this, a to b, c dx, so we can write it as c into x dA. So it is equals to c into b minus a, right? B minus a. So this is equals to 1, we know that, right? So by using this, we can take c is equals to 1 over b minus a, right? So using the property a, this property a, we know that the density is always greater than 0 or equals to 0, right? So if within the range a and b, within the interval a and b, if it is a constant, then outside that interval, it should be 0. The probability should be 0, right? So if we define fx as a constant within an interval a and b, and outside the interval it is 0, it has a uniform distribution of on the interval a and b, a comma b. So that is the uniform distribution, right? So we define it as this: a random variable x has a uniform distribution and it is referred to as a continuous uniform random variable if and only if its probability density is given by fx for the interval a and b. This is the probability, and elsewhere it is 0, where a, b are constant. So it's important a is less than b, right? The lower bound is a and upper bound is b. Okay, so the notation, it is x uniform. There are two parameters should be included. So x follows a uniform, continuous uniform distribution with parameters a comma b, right? So this is the graphical representation, right? X fx. So within the interval a and b, right? Within the interval a and b, the probability is a constant c. Elsewhere 0. See, in these regions, the probability is 0. So the area is a rectangle. That is why it's called a rectangular distribution. Right? So this is the graphical representation of the continuous uniform distribution. Right? So now we know the probability density function of x. Now we can find the cumulative distribution or the probability distribution function. Right? So how we find it? We integrate it from the lower bound to any arbitrary point. Then the probability density function pdf dx. Right? So we can do the rest. B minus a. So within the range a to any arbitrary point a, x. So then this is equals to x minus a over b minus a. So this is the cumulative distribution function or the probability distribution function. So we should write this properly. So the cumulative distribution function is 0 for x less than or equals to a. When x less than or equals to a, it's 0, right? So it's 0. Then cumulative up to this point, it is x minus a over b minus a for the range 0 to, sorry, a to b, not 0, a to b. And beyond that, it should be 1 since it is cumulative for x greater than or equals to b. So that this is the aggregate probability, right? So this is the cumulative distribution for the uniform distribution, continuous uniform distribution. Okay, right. So now we learned the probability distribution density function PDF, simple FX, and the cumulative distribution or the probability distribution capital FX of the continuous uniform distribution. So next we want to learn how to obtain expectation and the variance. And as we done before, nothing new here, nothing new. So we are going to obtain the expectation. So for that, we want to integrate from A to B, expected value of X into its PDF into dx. Right? Okay, try to obtain the expected value. Let's write this as A to B, X into Fx is now 1 over B minus A dx. Right? So obtain an answer after the integration. So this is the expected value of X, right? So in the same manner, please try to find variance as well. The answer should be this. So try to obtain that one. So this should be the variance of uniform distribution. Random variable of the uniform distribution X, right? Okay. Then you have an exercise, so show that the moment generating function is given by this one. Okay, so you know how to write the moment generating function, ETX into the function, distribution function, and then the density function, and then integrate it, and finally you should obtain this moment generating function. Do it as a homework. Okay, do this example. Show that if a random variable has a uniform density with parameter alpha and beta. So now in case of A and B here, it has alpha and beta. The probability that it will take a value less than alpha plus P beta into alpha, beta minus alpha is equals to P. So it gives that X is uniform distribution with alpha comma beta, and find the probability that X is less than this value. Do it. So it asks probability that it will take a value less than alpha plus p into beta minus alpha is equal to p. The probability that it will take the value less than the given value, right? So we integrate from the lowest point to the given value here. The function is now 1 upon beta minus alpha. So if we integrate this, x over beta minus alpha, and then we substitute the given ranges. Right, so it's alpha do this exercise. So you arrive into a building and are about to take an elevator to your floor. Once you call the elevator, it will take between 0 and 40 seconds to arrive to you. We will assume that the elevator arrives uniformly between 0 and 40 seconds after you press the button. Calculate the probability that elevator takes less than 15 seconds to arrive. Okay, do this example. Can you see this example? Can you see this?
Yes, ma'am.
Okay, try this. send me the answers. So it's a very easy one, right? Yes, you are correct. So you have to just substitute here. So here, the elevator take between 0 and 40 seconds to arrive, right? So there you have given the intervals of the uniform distribution. A is 0 and B is 40, right? A is 0 and B is 40. Then it says the elevator arrives uniformly, right? Uniformly between 0 and 40 seconds. So we can assume this as a uniform distribution. So it asks, once you press the button, calculate the probability that elevator takes less than 15 seconds. So you need to integrate from the lowest point to 15 seconds. So the probability density function is 1 over B minus A. B is 40 and A is 0. So once you integrate and substitute the limits, you get 15 over 40 as the answer, that is 0.375. The answer should be 0.375. Okay. So a very easy example. This should be the answer, right? Okay. So that is all about the continuous uniform distribution. Next, we move to the exponential distribution. No, limit should, it's not, someone has asked me, isn't limit 14? No, it's not 14. You have to put 15, right? 15 minutes. Check the ranges in the PDF function, then you can understand. Okay, then exponential distribution. Second one is the exponential distribution. So this exponential distribution is related to the Poisson distribution we discussed under the discrete distribution, right? It's related to the Poisson distribution. So in Poisson distribution, we considered the number of successors in a given interval, time or space. Right? If you can remember, in Poisson distribution, we discussed about number of telephone calls per week. So per week is the unit interval, right? And then number of typing mistakes in a given page of a book. Likewise, so number of successors in a given time interval, right? In Poisson distribution. So not only the number of successors, the waiting time between successive events are also random variables, but they are continuous, right? So in Poisson process, we can obtain the waiting time between successive events, right? In a Poisson process, if we consider the waiting time of successive events, it is a random variable, but it is a continuous one, right? So those kind of random variables follows an exponential distribution, right? So here we are considering about the waiting time in exponential distribution. Waiting time between successive events of a Poisson distribution. Right? So in exponential distribution, we concerning about waiting time, not only the number of successes, the waiting time between successive events. So it is a random variable and it is a continuous random variable, and that random variable follows an exponential distribution. Right? So now we are going to build up the exponential distribution function. Now let us find a probability model for the waiting time until the first success occurs in the Poisson process. Right? So here, let's first consider the waiting time until the first success. පළවෙනි success එක වෙන්න Poisson process එක පළවෙනි success එක වෙන්න කොච්චර කාලයක් ගියාද කියන එකයි අපි මේ දැන් බලන්න යන්නේ. Right? So we are going to build up the exponential distribution function. So before that, we are considering waiting time until the first success occurs in the Poisson process. Right? Consider that scenario. So let the Poisson process be given by, so if the Poisson process with lambda parameter, so during the unit interval or unit space, right, during the unit interval or unit space, number of success is lambda, mean number of success is lambda, right, this lambda, right. Then if we denote t, number of successes in an interval of t units. If it is 1 unit, the number of success is lambda. If it is t units, then it should be Poisson with lambda t. Right? Can you remember? We discussed it under the Poisson process. For a unit time interval, mean number of success is lambda for 1 unit. Then, so it follows a Poisson with lambda. It follows a Poisson with lambda. X follows a Poisson with lambda. And if it is t time units, then lambda t, that is x follows Poisson with lambda t. Right? So we know that Poisson process, Poisson distribution, we can write the Poisson distribution as e to the power minus lambda, lambda to the power x over factorial x. So if it is t units, then the process is e to the power minus lambda t to the power x over upon factorial x. So this is it. Right? So it is the probability of x successes in a time interval of length t. Probability of x successes in a time interval of length 1 unit is lambda. Probability of x successes in a time interval of length t, it follows Poisson lambda t. That is the concept here, right? So now we define a new random variable y. It is the waiting time until the first success. Waiting time until the first success. Okay, so now in order to obtain the exponential distribution, we want to find the probability density function of this y. Why? Because we say that waiting time between successive events is also a random variable. So that random variable follows an exponential distribution. So we need to obtain the probability density function of this y now. Okay, right. Okay, consider the distribution function of y, the random variable y. Simple fy is the probability density function. So we can obtain the probability density function by differentiating the cumulative distribution function. Under the random variables chapter, we learned that we can obtain the PDF by differentiating the cumulative one, right? By integrating the probability mass function, if simple fy, we can obtain the capital Fy as well, right? So since the waiting time is non-negative, so we are considering about the waiting time. So a time should be either 0 or a positive value, right? So for y less than 0, the cumulative should be equals to 0 since the waiting time can't be a negative value, right? So for y that is less than 0, the cumulative distribution function should be equals to 0. Now what happens when y greater than 0? Let's see. For y greater than or equals to 0, we can write the cumulative by the definition. Capital Fy is the probability where the random variable capital Y less than or equals to this simple y, the random variable, right? That is the definition of cumulative Fy, capital Fy, right? So we can write it as 1 minus probability of y greater than simple y. So that means in probability of capital Y greater than the given simple y value is the waiting time is greater than y. පළවෙනි success එක වෙන්න waiting time එක y ට වඩා වැඩි. මෙතන capital Fy වලින් කියන්නේ first success එක simple y ට වඩා අඩු කාලයකින් වෙන probability එක තමයි cumulative density එක කියලා කියන්නේ. So cumulative probability කියලා කියන්නේ. So we can අපිට ඒක ලියන්න පුළුවන් එක ඍණ probability waiting time is greater than simple y. So no issue there, right? So that is 1 minus probability of 0 successes in a time interval of length y. So we are considering about the first success. y when y වඩා වැඩි වෙලාවක් යනවා පළවෙනි success එක වෙන්න. ඒ කියන්නේ y කියන length එකේදී එක success එකක්වත් වෙලා නැහැ. 0 successes. Right? So according to the Poisson distribution, we can write it like this: 1 minus, right? The Poisson distribution is this for t time units. So in place of t, we can substitute here now y, time is y, right? So, sorry. Just a minute. Right? 0 successes in time interval of length y. So now we have to substitute 0 there. Successes, 0 successes means x is 0. Right? X is 0 now. 0 successes in length y. Okay? So it should be e to the power minus lambda y to the power 0 over 0 factorial 0. 0 successes. That means x is 0 within the time interval of length y. Right? So after simplifying it, we can write the capital Fy for y greater than or equals to 0 as 1 minus fy is 1 minus e to the power lambda y. So this is the cumulative distribution or cumulative probability for the y greater than or equals to 0. So now we want the probability mass function, right? So to obtain the mass function, we have to differentiate this. We have to differentiate this. So after differentiating this, we could obtain this probability distribution function, probability density function. Right, so this is the exponential distribution. Right, so for y greater than 0, the probability is lambda e to the power minus lambda y. Otherwise, it's 0. Right, so here the lambda is the parameter of the Poisson process. Right, so we write it in terms of theta for the exponential distribution. So there we denote theta is equals to 1 over lambda. Okay, so finally we can write the exponential distribution with theta that is equals to 1 over lambda using this PDF. And we can verify that y random variable is a probability density function. If we take all y, that means minus infinity to plus infinity. If we integrate this, it should be get the answer 1. Right, according to the rule. See here, it should be equals to 1. So we can show that y is a probability density function by taking the integration minus infinity to plus infinity, the given function. So here from minus infinity to 0, it is 0. Therefore, we integrate from 0 to infinity, lambda e to the power minus lambda y dy. Then integrate, and after substituting the limits, we get the answer 1. Right? So now we can define the exponential distribution. A random variable x has an exponential distribution and it is referred to as an exponential random variable if only if its probability density is given by, now in place of lambda we put 1 over theta. So theta is 1 over lambda. Lambda is the parameter of the Poisson process, and so exponential distribution parameter is denoted using theta. Theta is equals to 1 over lambda. Right? So it is lambda into e to the power minus lambda or lambda into y. If we substitute it by theta, we can write fx equals this distribution function. So this probability mass function, density function. අපි probability distribution කියන්නේ capital F x ට, mass function එහෙම නැත්නම් PDF density function කියන්නේ simple f x ට, right? So that is the waiting time x until the first success in a Poisson process has an exponential distribution with parameter theta that is equals to 1 over lambda. මෙතන මේ y කියප එක මෙතන මම x කියලා දාලා තියෙනවා. ඒ notation එකක් විතරයි එතන තියෙන්නේ, right? අතන අපි කියපු y කියන random variable එක මෙතන definition එකේදී අරන් තියෙන්නේ x කියලා. ඒක ප්‍රශ්නයක් කරගන්න නැත්නම්, okay? ඒකට හේතුව අපි කලින් x කියලා වෙන variable එකක් ගත්ත නිසා මෙතෙන්ට එන්න. So if random variable has x and x has an exponential distribution, it follows this probability density function. Right? So we denote the exponential distribution using this notation. X follows an exponential distribution with the parameter theta. So here theta is equals to 1 over lambda. Lambda is the parameter of the Poisson distribution. So the exponential distribution applies not only to the occurrence of the first success in a Poisson process, but also to the waiting times between successes due to the fact that occurrence of event in non-overlapping intervals are independent. So in exponential distribution, the Poisson distribution, occurrence of two events are independent. Therefore, this exponential function distribution applies not only to occurrence of the first success. පළවෙනි success එක වෙන්න waiting time එක විතරක් නෙවෙයි, right? ඕනම successive occurrence දෙකක් අතර waiting time එක හොයන්නත් අපිට පාවිච්චි කරන්න පුළුවන්. Not only the first success, right, but also the waiting time between successes due to the fact that occurrence of events are non-overlapping intervals are independent. First success එක විතරක් නෙවෙයි, ඕනම success දෙකක් අතර waiting time එක calculate කරන්න පුළුවන් මේ exponential distribution එක. Right? Okay. So this is the graphical representation of the exponential distribution. So it follows an exponential decay there. Right? This is the exponential distribution, the graphical representation. Okay. Okay, now next we have to find mean, variance and moment generating functions. Okay. So as before, expected value of x can be written as all x into fx dx. Okay. So 0 to infinity x into 1 over theta e to the power minus x upon theta dx. So we can take 1 over theta out. And 0 to infinity x into e to the power minus x over theta dx. So now here the integration by parts applies, right? If you can remember your A-level knowledge, x into e to the power minus x over theta, we have to use integration by parts. Okay. Okay, try to simplify this. So this is how the integration by part works, right? If you can recall the A-level knowledge of integration. So we can write the expected value now. X into e to the power minus x over theta dx. So by the integration by parts, we write this as x into e to the power minus x over theta. We apply the limit 0 to infinity. Minus become plus 0 to infinity e to the power minus x over theta dx. Okay. So by using the integration by parts, we come to the point here, x e to the power minus x over theta 0 to infinity plus 0 to infinity e to the power minus x over theta dx. So using this result, we can write this as minus theta e to the power minus infinity zero. So finally, we could obtain the mean waiting time or the expected value of x as theta. So if lambda is the mean number of success in the unit interval, then theta 1 over lambda is the mean waiting time for the first change. Right? So lambda is the mean number of successes in the unit interval. Then theta gives us, that is 1 over lambda, the mean waiting time for the first change or the first success. Okay. So we could find the variance as well. So to find variance, we need expected value of x squared. So expected value of x squared is found to be 2 theta squared, and then variance is theta squared. So you could use these two results when you finding the variance. Right? Try it at home. So the mean is, or mean waiting time is theta, and the variance is theta squared. The standard deviation is equals to the mean theta. So if you can remember in the Poisson process, Poisson distribution, both mean and variance equals to lambda is, right? As I remember. So here in the exponential distribution, mean is theta and the variance is theta squared. And the moment generating function, we can find the moment generating function by integrating from 0 to infinity. So it should be minus infinity to plus infinity. We put it as 0 to infinity because exponential distribution goes from 0 to infinity, right? For waiting time, there are no non-negative values. Therefore, 0 to infinity e to the power tx into the distribution 1 over theta e to the power x over theta dx. Right? By simplification, finally, you could obtain this result. Try this at home as well. 1 over theta t. to have exercise, obtain the mean and variance using the moment generating function. So you know how to obtain the mean and variance using moment generating function, right? By obtaining the derivatives and substituting suitable values, you can obtain mean and variance, right? Then median. So recall that median is given by M such that capital Fm equals to integration from minus infinity to simple m fx dx equals half. Right? That means we can find the median. Right? We can find the median by substituting from minus infinity to the median value. Right? The cumulative probability should equals to half. අපි aggregate probability එක ගත්තොත් minus infinity to median, the aggregate probability should be equals to half. Using that result, we can find the median. Right? So, this is the probability density function, and using the probability density function, we could obtain the distribution function. So it is 0 from minus infinity to 0 and 1 minus e to the power x over theta for x greater than 0. So this is the cumulative probability or the probability distribution function, as you can remember. Right? අපි ඒක හොයලා තමයි density එක ගත්තේ. See here. This is density. So here it is this is the cumulative probability, right? එහෙම නැත්නම් ඔයාලට මේක integrate කරලා ගන්න පුළුවන් cumulative density function එක using the PDF, probability distribution function. Right? So, if we want to find the median, then according to that formula here, we can write the probability distribution function. So it should be 1 minus e to the power, in place of x we substitute now m, the median, over theta should be equals to half, that is 0.5. Right? So e to the power minus m over theta, it is equals to now 0.5, and we can find the median minus theta into log 0.5. So this is the way we are finding the median of exponential distribution. Okay. Any questions up to now? So now we learned the exponential distribution. In exponential distribution, we are concerning about the waiting time, right? So waiting time between successive events. So waiting time follows an exponential distribution. So we found the density function of the distribution. This is the density function, and the way the graphical representation of the exponential distribution, and mean, variance, and moment generating function, and how to obtain the median, right? So there are some useful results in this exponential distribution. So the first one is probability x less than 2x is, we can find it using integration from 0 to any arbitrary point x, right? So it is then the integration of the density function. So it is equals to 1 minus e to the power minus x over theta, right? Then probability where x greater than simple x is 1 minus the probability of capital X less than or equals the x value. So 1 minus e to the power minus x over theta, it becomes e to the power minus x over theta. And then, right, can you remember the geometric distribution? We discussed a property that the no memory property. The no memory property, right? Can you, I think you can remember, we discussed under the geometric distribution. Geometric distribution එකේදී අපි කියන්නේ පළවෙනි success එක වෙන්න තිබුණ trials ගන්නනේ. එතකොට පළවෙනි trial එක වෙනකම් අපි x කියලා trials ගානක් ගත්තොත් ඒ x වෙනකොටත් පළවෙනි success එක වෙලා නැත්නම් x plus t කියන time එකේදී success එක වෙන probability එක අපි calculate කරා මතකද? එතකොට ඒක x කියන time එකත් එක්ක dependent වෙන්නේ නැහැ, depend වෙන්නේ නැහැ. එතකොට ඒකට අපි කියනවා no memory property කියලා. Here also the exponential distribution has no memory. It is called no memory property, right? That is probability x is x plus t given that capital X is greater than simple x. X වෙනකොටත් success එක occur වෙලා නැහැ. නම් x plus t වෙනටත් වඩා වැඩි වෙලාවක් ගන්න එක. Right? So it is equals to p greater than px greater than t. So it has no memory. We can prove it in the way we prove the no memory property in geometric distribution, right? So refer to that note and try to understand this. The same scenario as the geometric distribution, this exponential distribution also has no memory, right? Okay. Now go through these exercises. First try to get these answers. Then I will explain, right? Take 5 minutes time, or you may take 10 minutes. It's now 12:10 now, so 12 past 10. So you can take 9 minutes